Okay, so we are live now, and it's my great pleasure to introduce to all of you Bruno Sansó. He's originally from Venezuela, but he has been in the US for a few years now, to be very polite, some time, right, Bruno? And his academic career is spotless. I'm pretty sure many of you know his career. He has advised many students, many papers with a lot of impact, not only in the good journals, but meaningful papers that do some changing in research. And he has been very active researcher. And for us, this online system, provide us the chance to have someone of his side to talk to us and give a presentation. So we are very happy to have you, Bruno. He has also been editor of Bayesian Analysis. That is also a big job, I'm pretty sure. And he's a very active Bayesian. So I'm very happy to have you here with us, and it's our pleasure that you accepted to give this talk. I'm curious to go through the details of your paper. It's one area that I'm interested myself a lot. So thank you for accepting, and the word is all yours.
Great. Hey, thank you, Marcos, for that very nice introduction. Well, first of all, I'm going to apologize for speaking in English. My Portuñol is really poor these days. I mean, I haven't had a chance to go to Brazil in a long time, and I miss that. I mean, I wish I had the opportunity to be back there one of these days, sooner, visit all my friends and former students and stuff like that. So anyway, you're gonna have to deal with my English. I'm not familiar with this platform, so I don't quite know how it works with the interactions with the audience. But Marco, if you need to interrupt me, just please do. And well, there we go. We are gonna be sharing the screen, I guess. Entire screen. Share.
There we go. Your screen is there. Perfect. We can see.
Okay, good. So that is a picture of myself when I had a little bit more hair than I have now. And that is the title of the talk that I am going to be giving today. It's about non-Gaussian geostatistical models. And the core of this model is the use of nearest neighbors processes. Right, and I'm going to tell you all about those processes and why it is important for us and all that stuff. Anyway, this is from me, but of course I have collaborators, and they are the people who really did the work. In particular, this one, Xiaotan Zheng. Xiaotan Zheng is the former PhD student who did essentially all the work. And so anything that you don't like, talk to me. Anything that you like, talk to Xiaotan. To talk to Xiaotan, you're actually going to have to go pretty far, because he is now doing a postdoc with Noel Cressy in Wollongong down in Australia, and doing pretty well out there. Anyway, and there is also another colleague, one that actually sits in the office next door to me. That would be Thanos Kotas. And well, so it was essentially the three of us who did this work. Good. Now, motivation. So I've been obsessed with the idea of processes for non-Gaussian data for quite a while. I mean, I've been interested in things like extreme value theory, and extreme value theory essentially has to do with non-Gaussian processes. I've been interested with quantile regression and quantile processes. And again, what happens there is that you're dealing with non-Gaussian processes. And so this has been something that has been ongoing in my research for quite a while. But then with this piece of work, we are actually committing to creating a whole family, if not a whole framework, of models that can really tackle non-Gaussianity in a very comprehensive way for large spatial data fields. Okay, and why non-Gaussian? I mean, at the end of the day, if you have any experience fitting Gaussian processes, you will know that Gaussian processes are extremely flexible and that they adapt very well to all sorts of irregularities, right? Even non-Gaussianity, right? And so why do we really have to push the envelope? Well, because sometimes even the flexibility of Gaussian processes is not enough. And in particular, when you're thinking about what the generative process is and how you're going to be predicting new observations, you need to account for the fact that there is no Gaussianity there. Okay, so here's an example. This is albedo reading. So what is albedo? Albedo is the reflectance of the Earth. So light from the sun comes into the Earth and gets reflected. This is a very important property. In particular, it's very important for climate because the more light you reflect out there, the least heat you are containing in the surface of the Earth, and so the least warming you have. And so albedos are reflectances, and those reflectances are actually a percentage, and they are bounded between 0 and 1 because they are percentage. So the natural reading of albedo is a variable between 0 and 1. Now, this is an example where we are looking at two satellites that are measuring albedo. One is looking from 135 degrees longitude. The other one is looking from 75 degrees longitude. And in this case, they're looking at North America. And well, there is, when you put together these two satellites, this is data for just one day. And it corresponds, when you put them together, it corresponds to about 600,000 observations just for North America. And so that essentially says that we are talking in the millions of observations, right? When we're looking at, the whole Earth and stuff like that. So large data, non-Gaussian, because clearly these are bounded between 0 and 1. Large data, non-Gaussian fields. Okay. Now, another example of non-Gaussianity. One of my favorite topics, sea surface temperature, okay? Sea surface temperature, well, yeah, we model it as Gaussian, right? But fields of sea surface temperature are very nonlinear. And I've had this discussion, particularly with Noel Cressy and Chris Weichel, about, do we really need nonlinear models? Or is it that we need non-Gaussian models? I mean, what is the interplay? Is it non-Gaussian or nonlinear, or both non-Gaussian and nonlinear? But I've always had the idea that the reason why people find the need to nonlinearity is because they stick to Gaussianity, right? I mean, they have these first two moments in their minds, and they cannot escape that, and that's why they end up having to go into more complex models and stuff. And, SST is an example of that. All right, great. So two examples of non-Gaussianity. Now, radical non-Gaussianity, counts, okay? So if we go into counts, and the counts are not very high, so that we cannot approximate those counts with a normal distribution, then, well, we are clearly in either Poisson territory or negative binomial territory, that kind of stuff. And of course, that's non-Gaussian. In particular, these are discrete data. So, there you go. That's yet another example motivating the idea of non-Gaussianity. Well, so with that, I'm not going to claim that I am the first guy that has come up with the idea of modeling non-Gaussian random fields. By no means. I mean, the literature is out there. There are very many different approaches to dealing with non-Gaussian data, right? One of the favorite approaches in the literature is the one that is based on modeling some distributions that have heavy tails and maybe skewness as mixtures of location and scales that are essentially normals. So you take a normal, you look at the location of the normal, you look at the scale of the normal, and then you assume that that location and that scale is random, and you mix those normals with some distributions. And that produces, spherical elliptical distributions, skewed distributions, skewed T distributions, all sorts of things like those. And those things have been extended in order to cover the topic of random fields. Now, the other possibility is, well, what about you transform, right? So you take, we learned the box and Cox transformation a million years ago. That is just an example of what you can do. Those things have been extended. So you take a transformation of the data and then you model them as Gaussian, right? Then, there is the whole big area of copulas out there, right? So the idea of a copula is that it allows you to do a very flexible modeling of a multivariate distribution whose marginals you fix. So you fix the marginals, and then the structure of the dependence is expressed by a copula. And those things have been generalized to the infinite dimensional case so that you can get processes. Then there is, well, okay, so we're Bayesians, and we can bite the bullet of going full non-Gaussian by essentially using a mixture model, right? So we can use a mixture model. We can make the mixture model dependent on location. And there you go. You have a spatial mixture model that can deal with non-Gaussianity. Then there is one that is very popular these days because basically it's part of INLA. So it's being coded into INLA, and it's the SPDE approach. So the SPDE approach, well, I don't know if the one that it's encoded in INLA deals with, maybe now it does, but it didn't at the beginning, deals with the non-Gaussianity. But the idea is that a random field can be expressed as the solution of a stochastic partial differential equation. And if you are clever about solving that equation, you can do it really fast, essentially using a sparse basis and some approximations like INLA. And if you force that solution with a noise that is non-Gaussian, then you get a non-Gaussian random field, right? And basically, the idea is that you're going to go back to the skew distributions that we talked about at the beginning. Then there is yet another area, and that is very important in order to deal with discrete data and counts and binary data, which is a generalization of the GLM models, right? So a GLM with spatial effects, and this GLM with spatial effects will give you a spatial field with non-Gaussian observations. Good. So those are essentially, well, I mean, hey, I'm sure I am forgetting the one that you like the most and the paper that you wrote about that particular way of doing things that is possibly a combination of one versus the other. But what I see from of that whole list that I put up there is that in essentially all those cases, somewhere there is a Gaussian process underlying the modeling, right? Somewhere there is a Gaussian process underlying the modeling. Maybe the only exception is the SPDE, where there isn't really a Gaussian process anywhere, maybe. But you transform and you convert the problem into a Gaussian process. That's essentially the whole idea, right? We want to do something different. We want to go in a completely different direction to avoid having to deal with modeling a Gaussian process at all, if possible, of course. Okay, now, something that people have done for quite a few years now is, well, the likelihood of a Gaussian process is a big beast. It's a complicated animal to deal with. And the reason why it's a complicated animal to deal with is because you have to build a likelihood that requires order n³ operations to calculate at every iteration of whatever algorithm you're using in order to fit your parameters, right? Because you need to decompose an n by n matrix, and that is going to take you n³ operations. How to avoid that? Well, one of the most successful and popular approaches these days is the idea of using a quasi-likelihood, where instead of using the whole dependent structure, you use only a limited dependent structure, right? So you look around and you choose your nearest neighbors, and by choosing your nearest neighbors, you essentially come up with a pseudo-likelihood, right? That's called the Vecchia approximation. Now, unfortunately, you cannot just do it like that, because if you do it like that, you end up with something that doesn't really produce a coherent joint distribution. So you have to pay a price. And the price that you pay is you have to lay down a reference set, you have to order that set, and then once you order that set, then you have a proper joint distribution that you can build using the nearest neighbors within the ordering of that set. So Vecchia approximation has two components. The first one is you take your observations and you order them somehow. Now, once you've ordered, then the second component is the component of the neighborhood. You build a neighborhood of a certain size given the ordering. So you are not looking at neighbors that are not in the past of your ordering, right? So only in the past of your ordering is where you're going to be looking for your neighbors. That gives you the Vecchia approximation with a pseudo likelihood. And well, if you happen to be a Bayesian, you just use that thing, plug in your prior, and off you go. And there is theory about that. I mean, Ben Shabby, for example, has a beautiful paper on how to do Bayesian statistics with pseudo likelihoods and stuff like that. Okay, so there you go. Nearest neighbors, Vecchia approximation. A lot of people are doing that kind of stuff. And so instead of using the full joint distribution of the vector z sub s, you are using this approximated distribution that is based on this ordering and neighborhood structure. All right. For a lot of very insightful papers on these kind of things and also software, look at the literature that has been written by Matthias Katzfuss. He is definitely one that has contributed substantially to this area. And this is, you know, graphically how it works. I mean, essentially, you have a point here in blue, and you are looking at the neighbors, but those neighbors must be labeled before the label that you have. So this label is the label 54. So even though this number 58 is closer than maybe 53, you cannot use it in the neighborhood because it is ahead of 58 in the neighborhood structure that you've created. All right. So, and that, of course, is a limitation because everything you do is going to be conditional on the ordering that you impose. All right. That's one thing that you need to be aware of. We can discuss that issue a little bit more later. Anyway, now we don't want to do Vecchia approximation. I mean, Vecchia approximation has been done. You can read, but we want to leverage this idea of the neighborhood structure. Okay, that idea has actually been leveraged by a very nice paper by Data and Banerjee into something that is called the nearest neighbor Gaussian process. So in that paper by Data, they extended the idea of the Vecchia approximation and they turned it into a process. So it's an actual proper spatial process that they create. Vecchia approximation is an approximation to the likelihood. There's nothing about a process there, right? It's just a matter of approximating a joint distribution. A NNGP, it's a process. It's a spatial process with it satisfies all the characteristics. So it's an infinite dimensional entity. Okay, good. Now, what are we gonna do in order to create a neighborhood, right? Or a distribution for neighborhoods? Well, we are going to use this process that we call a mixture transition distribution model, on which we wrote a paper, and it has some very interesting properties. Okay, the idea is the following: it's a mixture process, right? So it's a mixture distribution. So what you have here is the following: suppose you have your reference set, right? And within your reference set, you have an ordering. Within that ordering, you created a neighborhood. Okay, now for those neighbors, what you are going to do is you are going to write the conditional distribution of your process at the given location that you're looking at, and you're going to be conditioning on the neighborhood, right? So SI conditional on the neighborhood of all the guys around SI. And that conditional distribution is going to be modeled by a mixture. Now, in the components of the mixture, you're only looking at conditionals that use one element at a time in the neighborhood. So your conditioning here, let's say you have a neighborhood of size 10, you are conditioning ZSI on 10 neighbors, but each component of the mixture is actually looking at one neighbor at a time. And then there are some weights, right? That's what it's called a mixture transition distribution model, okay? I am not specifying anything Gaussian here, right? This F can be any kernel you want. It's just a conditional density for SI given one neighbor. And of course, this must be weights. And because they're weights, they have to add up to 1 so that you actually have a proper density. Okay, great. So now we are in business. We can use this scheme in order to define a process, right? Why? Well, because we can actually extend the definition of this thing to any point in the domain. We don't need to have points in the reference set. So, you have your observations. Your observation constitutes your reference set, although you can have any reference set you want. I mean, you can have a subset as a reference set, but usually you have all your observations is your reference set. Now, to have a process, you have to be able to extend the distribution to any point in the domain, right? Because essentially the definition of a process is that you can build any finite dimensional multivariate distributions for any point in the domain. Now you can do that, right? You can do that by essentially integrating out the points that are in the reference set, okay? So what this means, this is actually very nice because it not only gives you a definition of a process, it actually also integrates out the reference set. And by integrating out the reference set, the ordering that you used in order to build your original joint distribution is gone, right? And so it's not needed. So for predictive processes, like the processes that we're defining here, the ordering becomes irrelevant, okay? To fit the model, you need the ordering because, of course, to create a likelihood, you require a joint distribution on the observations that you observe. And for that, you need the ordering. So inference is going to be order dependent, but prediction is not, because in order to define your process, you integrate out the reference set, okay? And that it's a very nice thing, okay? Well, the process that we've created, we call the nearest neighbor mixture process, or NNMP. So as opposed to NNGP, which is the NN-Gaussian process, we extend the NNGP to an NNMP. Now, I'm not sure, and I have tried, but I'm not sure that the NNGP can be obtained as a special case. Maybe in expectation, but I have not been able to find the NNGP as a special case of the NNMP. Probably can be, but it would be very, very peculiar. Good. Now, why is this process interesting? Well, this process is interesting because of the following property. Essentially, what you need in order to define this process is a collection of bivariate distributions. So remember, each element of the mixture is a conditional distribution. You can obtain that conditional distribution from a bivariate, right? So this is the conditional distribution that is the elf element of the mixture. Now you obtain that as the ratio of a bivariate distribution divided by a univariate distribution. So in order to define the conditional kernels in each one of the components of the mixture, you are going to need a bivariate distribution. So our process is defined by collections of bivariate distributions. Now, the beauty of this thing is that if you take these bivariate distributions in such a way that they have pre-specified marginals, right? So if the marginals are all the same here, so the marginal for the Lth component doesn't depend on L, right? If the marginal of the Lth component doesn't depend on L, and so see, if all these bivariate distributions have the same marginals, then that marginal is the marginal of the overall process. In other words, you want to have a process whose marginals, it's a spatial process, but you want to have one whose marginals are Poisson. Well, all you need to do is you need to consider a bivariate family of distributions whose marginal is Poisson, right? And then plug them into our formula for an NNMP, and that will produce a Poisson marginal process, right? That is essentially the idea. And that's the beauty of this thing. So what marginal do you want? Well, any margin. Dream of a marginal. Skew T. Okay, you want a skew T marginal. Well, find a family of bivariate distributions whose marginal is a skew T. Find the corresponding conditional distribution and use that conditional distribution into the formula for the NNMP. That's it. So that's the beauty of this whole story, right? And this is what we have in this slide. To build an NNMP with a desired family of marginal, say Poisson, skew T, normal, whatever you want to come up with, you consider a bivariate distribution with marginals that are GS, obtain the resulting conditional distribution, use that resulting conditional distribution as the component of the mixture, right? You only need to solve a bivariate problem. So the problem of creating a non-Gaussian process is usually very difficult if you consider it without any transformation to Gaussianity, because you need distributions whose multivariate expressions are tractable, and that is not very easy to deal with. It's not very easy to find. Now, we avoid that problem by essentially reducing the problem to dealing with bivariate distributions. So we don't need multivariate distribution of arbitrary size. We need just bivariate distributions to define our process. And that's the beauty of this whole thing. Okay, great. What do you lose? Well, what you lose is that you don't really understand the full multivariate story, right? Yes, that's really the problem. I mean, what is the multivariate distribution that you are creating through this process? Well, it's a mixture. And by making it a mixture, you hope that it's going to be very flexible and it's going to pick up a lot of the possible variability in the data, but you really have no control about it. And sure, that's the shortcut. Now, here's an example. You want a Gaussian NNMP. So you want a process that is spatial and whose marginals are Gaussian. Well, you start with a bivariate Gaussian vector, right? Bivariate Gaussian vector is going to have a bivariate, a 2x2 correlation matrix, right? A covariance matrix. We express that covariance matrix like this. Remember, one of the conditions is that the marginals are the same, right? So the marginal for U and the marginal for V has to be the same. So that's a condition here. Fine. So then we create the conditional. The conditional, of course, is given by a conditional of a bivariate marginal, of a bivariate Gaussian distribution, which is very, very straightforward. And that's the formula there, right? Now, that would be the component of your NNMP. We can make it even more flexible because we can make this correlation here, this correlation parameter that depends on L, we can make it dependent on location. And we make it dependent on location by taking something like an expression like this, which we know it's a valid correlation in space. And then now we have the extension of this conditional distribution to a space-dependent conditional distribution that looks like this. And so now our model is actually adapting spatially. So not only we have something non-Gaussian, we also have something non-homogeneous, right? With the right marginals. You want a skew Gaussian distribution as the marginal. Well, you start with a trunk. I mean, what is a skew Gaussian? A skew Gaussian is a location mixture of a Gaussian. Now you leverage that. You take the mixing distribution to be a truncated normal. Now you take a bivariate Gaussian vector with a certain location parameter, and you mix that location parameter. Okay, this is the mixing going on, and that gives you the formula for the conditional density. You can extend this thing to be non-homogeneous by essentially making the correlation of the Gaussian space dependent like before, and then, well, that's what you have. So it's very easy to obtain a skew Gaussian marginal process in this way. Okay, now you can use copulas. Why not? Well, you just need bivariate copulas, because all you need to do is to obtain a bivariate distribution whose marginals you can control. Now, copulas in a bivariate setting are very, very easy to deal with, right? Gaussian copulas C with correlation rho L, for example, beta marginals. So let's say we want a beta marginal for the albedo data. Now we are going to obtain a joint density that is given by the derivative of the copula times the product of the marginals. And then from there, we can obtain the conditional component that goes into the mixture. And then, of course, we can generalize things to make them non-homogeneous by making the correlation of the Gaussian copula spatially varied. We can play this game for all sorts of distributions. Gumbel copula with gamma marginals. Well, okay, there you go. You have a Gumbel copula with gamma marginals there. Gaussian copula with negative binomial marginals. Same idea, right? So you can have a negative binomial marginal process. The other component of this thing is the weights. How do we deal with the weights? Well, in order to deal with the weights, we essentially need a distribution because the weights are probabilities. So we start with a distribution, okay? A distribution could be a logit, okay? So if we have a logit, we can make that logit dependent on location because a logit essentially has a Gaussian distribution somewhere. And so we can essentially make the parameters of the Gaussian distribution dependent on, say, longitude and latitude. All right, then we take some cutoffs. In order to define the cutoffs, we are going to need a kernel. So we define the kernel, obtain the cutoffs. From the cutoffs, we actually obtain the probabilities. And then those probabilities, right, correspond to the weights. And those weights are the ones that I'm going to be putting into my mixture, right? If you take G, if you take the regional distribution to be a uniform, then basically you are reproducing the kernel that you use for the cutoffs in the weights. And so that's a very straightforward way of doing things. Okay, great. Now, the tuning parameters of this process. What are the tuning parameters of this process? The ordering, but we discussed it. I mean, the ordering is necessary only for the likelihood, not for prediction, okay? What do we do about it? Well, it's been studied, and essentially the best way to go, I mean, there is a paper where they came up with an algorithm and blah, blah, blah. Seriously, just take it random. So an random ordering basically works fine, right? And the algorithm that they produced in that paper, it's not always better than just random ordering. The other point, though, which is a lot more important, is the size of the neighborhood. Well, what do you do about it? Well, that's a tuning parameter. You're going to have to choose it. You can choose it after the fact, right? For example, you can do some cross-validation, or you can do some scoring, or you can do some model comparison by choosing the neighborhood. Don't try to pick it random, because, I mean, if you put it as a random thing, hell breaks. I mean, you're going to be running a reversible jump thing and blah, blah, blah. Okay, fine. Monte Carlo. We do Monte Carlo. It's fast. Why is it fast? Because it's a mixture. So you break the mixture. Okay. It's not horrifically fast. No, we are not able to run 1 million data points, right? I mean, unless we want to wait for days. But it's fast. And so, yes, we can handle tens of thousands of points in a decent amount of time. Fine, here are some simulations, but I think I'm going to skip through this because I actually want to go into the more interesting real example, right? Which is this data set, one of my favorite data sets. I mean, if you want this data set, I can give it to you. It's a very challenging thing. This is a Mediterranean sea surface temperature collected in situ by different types of devices, right? Most of them are ships cruising the Mediterranean and letting water into their engines and measuring the temperature of the water as it goes into the engine. That's the most common device, but there are other devices. There are buoys that are floating around. There are buoys that are just stable, stationary, they're taking samples at regular intervals and things like that. And so this is how this looks. Very heterogeneous data set, right? And not only is it a heterogeneous data set, is a heterogeneous data set that reflects a very complex nonlinear field, okay? Now, on top of that, we have the Mediterranean basin divided in 1, 2, 3, 4, 5 different seas, if you want, that have oceanographic differences, right? And this has been justified in papers by these experts. And when we look at the distribution of this data, they look nothing but normal. They look very slanted, so they are skewed. And the skewness seems to depend on the sea within the Mediterranean where we are looking at the data, okay? Right, and so we have essentially a distribution like this, right? You can see the different basins in the Mediterranean looking kind of different in terms of the characteristics of their distribution, okay? This is after removing the mean and making the mean dependent on longitude and latitude and stuff like that. Okay, so different skewness for different basins in the Mediterranean Sea. All right, so challenging data set, lots of heterogeneity, non-Gaussianity, right? Because we believe that this is essentially skewed data, but the skewness seems to depend on the geographical location, right? So, lots going on. And so what we want is a skew Gaussian marginal, and we want that skew Gaussian marginal to have a skewness parameter, this lambda, that depends on S. So that depends on location, okay? So that's the Gaussian, that's the marginal that we're gonna want to have. Now, is that easy to do? Well, yes, we can do it because essentially you build it in the way I told you to build it. I mean, you need a bivariate skew Gaussian, and you build a bivariate skew Gaussian by taking a Gaussian and mixing the location with a truncated normal. And that, it's easy to implement. From an MCMC point of view, it's just a matter of introducing the right latent variables in the right places, okay? Good, now the skewness parameters in this case are just going to be 5, right? And, well, we fit the model. And once we fit the model, we actually have the inference for those 5 skewness parameters. And you can see that there are significant differences there, right? Most of the skewness parameters are very highly negative, but some of them could be pretty, I mean, the Western basin, for example, could easily have a skewness parameter that is significantly that is essentially 0, right? But you can tell that there is a difference there in the values of these guys. So this modeling actually has a sense. All right, now the kind of results that you're getting when you put this all together and you are creating a unique, I mean, it's not 5 different spatial fields. Because of the mixing and the neighborhood averaging, you actually come up with just one unique random field for the whole Mediterranean. And this is how it looks when you do that. And this is how the uncertainty bounds look when you do that. I mean, of course, we are doing a fully Bayesian inference for this thing. We have full uncertainty quantification of the predictions that we are coming up with here, right? Let me see, how much time do I have? I guess, Marco, correct me if I'm wrong, but I guess I have still at least 5 minutes. Is that correct?
10 minutes, fine. Yeah.
All right, good. So, plenty of time. Right, this is another example. In this example, we went completely non-Gaussian in the sense that these are counts. These are bird counts. I mean, there is a very nice database of bird sightings for North America that gets updated every year, right? And so you have monthly sightings, and it's publicly available. And well, I mean, you can just load the data. It's very important for people studying bird species and their evolution, because it's been ongoing for more than 20 years. And so in this case, we're just looking at one snapshot of it's available for the whole continental US and Canada, I believe. Maybe northern Mexico, but I'm not 100% sure. But for sure, continental US and Canada. I don't know. I'm saying Canada, but I don't see Canadian data here. Well, okay, I'm going to say it's available for the whole continental US, for sure. Sorry about that. Anyway, this is a snapshot of 2019 for a bird species that is prevalent in the American East. Okay, so it's just one specific species. Okay, and in this plot, what is happening is that the circles are essentially proportional to counts. All right, good. And so the bigger the circle, the larger the counts, and of course there is the color coding of the counts, and so you go all the way from very close to 0 to, I mean, if it's 0, then there's no sighting, right? But essentially from very close to 0 all the way to 150. Okay, great. So those are counts, and we can model this thing with a spatial process whose marginal is a discrete random variable, right? And what we use is a Gaussian copula, right? But the marginals are going to be negative binomial. And of course, you want them to be negative binomial and not Poisson, because you can imagine that there is all sorts of overdispersion in this kind of data. Okay? So negative binomial marginals, Gaussian copula, right? And remember, all you need to do is you need to define your bivariate distribution, right? And from that bivariate distribution, you obtain your conditional distributions. And you are guaranteed to obtain a marginal negative binomial for the whole field. Okay, we are using latitude as a covariate. Longitude didn't show up to be significant, and so there's only one covariate here, right? The copula is actually spatially varying, so the Gaussian copula has a correlation that is spatially varying. And, you know, we can fit the data, we can obtain the results, and so we can have a nice, smooth, predictive field. And of course, we can have the uncertainty quantification that goes with those predictions. In this case, you know, 95% width of the predictive intervals for the whole thing. And that gives you an example of discrete data spatial fields, right? One of the beautiful things about this neighborhood structure is that it is very easy to come up with an analysis of residuals, right? Because of the neighborhood structure, you can actually claim that a transformation of the residuals will provide you with something that is uniform. So you can do QQ plots to compare with the uniform in the very same way that you do for autoregressive time series. So, essentially the beauty of these models is that they look a lot like an autoregressive model, right? And so you can use some of the methodology that you use in autoregressive time series models to analyze things like goodness of fit and stuff like that for spatial models. Okay, well, that gives you an idea of residuals, and you can do the whole analysis there. Okay, computations, I mentioned it very briefly. They are performed with the MCMC. We leverage the mixture and the local structure of the model. There is a lot of parallelization that can be done. Most importantly, and that is the key, absolute key issue of this thing, we never invert a matrix that is bigger than L by L, right? That's the worst that can happen to you, but usually it's just 2 by 2, right? So large matrix computations are absolutely avoided and exist nowhere in this thing. And a lot of the matrix inversions can actually be preloaded, right, if you have the right model, but that will depend on the model that you build to make things much faster. Okay. Yes, you pay a price. The price that you pay is that you have to introduce a lot of latent variables. What that means in terms of computations is that you do have a substantial memory footprint, right? And so you have to handle the memory in a good way. As I said, residual analysis can be performed using local conditional structure, and that's very nice. You never have to do, if you're familiar with copula models for large spatial fields, you will know that the big issue for copula, especially for discrete copulas, and well, there's a whole deal with the discrete copulas. I can talk about that later if somebody asks me about it. There is multivariate integration that is required, and usually that integration it's difficult to deal with, and there are all sorts of tricks. We have nothing of that. I mean, we only need, if we need to integrate anything, it's in a bivariate setting. Okay. All right, conclusions. We have a general framework. I mean, it's not even a family. It's a completely general framework for an effective statistical model of wide families of non-Gaussian processes, right? You have a lot of flexibility because of the mixture structure, right? And you can go non-homogeneous, right? You have a sparse structure that can be leveraged for parallel computations. You have a pretty scalable approach, although MCMC is always limited in terms of scalability. And in fact, one of the things that we're doing right now is considering extensions that use a variational base in clever ways, because at least so far, our experience with variational base provides orders of magnitudes of speed up. And so that's basically where we're going next. But importantly, we obtain a fully probabilistic quantification of the predictive uncertainty. And one of the beauties is that we model everything on the original scale of the data. So we do no transformations. And you may ask, why do I care about doing it? I mean, why is it so bad to do transformations? Well, because transformations deform the properties of the field. And so you are doing a nonlinear transformation that may dilute the correlation structure. And so in your latent process, you may end up needing a very, very, very strong correlation in order to be able to express that association at the level of the observed variables. Because we don't have that transformation, we don't have that issue, right? We are on the original scale of the data. And I can tell you about that because, one of the non-Gaussian obsessions of my life was modeling rainfall. And my way of modeling rainfall was by putting one or maybe even two Gaussian processes underneath. And the truth is those processes had to have an extremely, extremely strong correlation in order to capture even a weak correlation for the field of rainfall that we were observing. right? Which is a little bit of a drawback because, you know, it's kind of a weird modeling thing. Now, references for this thing. Well, we have an original paper where we did model this for the temporal case, and that has been out for a couple of years already. It's a paper on MTDs, mixture transition distribution models. Then we wrote a paper for the continuous variable case, and that paper is currently under revision. Hopefully will get published pretty soon. And then we have another paper. I mean, the area was so large that we decided to split the presentation of these models into two, one for the continuous variables and one for the discrete variables. The discrete one is actually already been accepted in environmetrics. And so it will be appearing in environmetrics pretty soon, I hope. And that is my talk. Thank you very much for your attention.
Thank you, Bruno, for the very interesting talk. I'm pretty sure you have some questions here already from the audience, and I have questions myself. So let me start with the audience. Vinicius is a professor here at the department, and he works with the spatial statistics as well. So I think you can see on the screen, right? He's asking how neighborhood is defined. Do you suggest any criterion to select these neighbors, and how to say it's the number of neighbors a problem in any sense?
Okay, so again, to define the neighborhood, the first thing you do is you take your reference set and you put an ordering. It's an artificial ordering on your reference set. Now, once you have that reference set, then what you do is you fix the number of neighbors, and you take the closest L locations to the point within the reference set, right? So you have your, let's say you have a neighborhood of size 3, and you are at the location number 10. Then you are going to be looking at the previous 9 locations and taking from those 9 locations the 3 closest ones. Right? That's how you build your neighborhood. This is not peculiar of our model. This is what all the nearest neighbors models and all the Becky approximation models do. Okay. Then okay. Then there is the problem. How do you choose L? Okay. So how do you choose the size of the neighbor? Yes, it is an important parameter. So because I'm Bayesian, my first temptation would be, oh, you take L to be a parameter and you estimate it. Hell breaks, right? Because then you have a mixture with a random number of components. And sure, I'm pretty sure some of you who are very, very good with their MCMCs can do it. But you are going to be running the reversible jump thing. It's going to be hell.
Is it still a valid process if the number of neighbors change throughout the process? I'm not even sure if you can show the Kolmogorov properties there, because then once you fix, yeah, well, I think that the proof kind of relies on that somehow.
Maybe you're right. Maybe it's even worse than I'm thinking. Maybe it's not even a valid process anymore. So anyway, don't put it random. I don't know. Maybe somebody can study what happens when you put it random. But we didn't. We fixed it. And then what do you do? Well, okay. So there are 2 approaches here. One approach is, well, you be conservative, right? Take a very large L, which you're going to pay a price with your with your computations, because of course the larger the L, the more computations you have to do. But you can choose the structure of your weights in a way that they essentially kill components that are not needed, right? And so that is a possibility. So you take L equals, I don't know, 50, 200, a large number, and then you let the weights have a probabilistic structure that essentially applies the jackknife, right, with the right priors. You can do that, and that's how we usually do it in time series. In spatial setting, it's a little bit harder because the computations end up killing you big time. So what we do is we go low and increase and then choose based on some scoring. My favorite score, CRPS, okay, continuous rank probability score. And or you can use DIC, you can use PPLC. I mean, any score you like that it's a good predictive score. So you use the predictive score, and then you choose the L based on that predictive score. Another possibility is you use base factors. I mean, of course, hey, if you want to be, the true base. But that's how we do it.
He has another question. You mentioned that
Yes.
the bivariate distributions are necessary to build the NNMP. Then you present several examples. Is there any case that cannot be considered in this context, or you can always, as long as you have the bivariate distribution, is this a valid process?
Okay. So as long as you have valid conditional distributions that are such that the marginals are the same, right? So the important part is that the marginals are the same. I mean, in your bivariate thing, the marginal for one component and the marginal for the other component need to be the same. If they are not the same, then the theorem that is not valid. You are building something that is probably going to be a valid process. You have no idea what the marginal distribution of that thing is. So the only way to guarantee the marginal distribution that you want is to take a bivariate whose marginals are the same. Now, you give me any marginal, and I can always come up with a bivariate, a valid bivariate, whose marginal is given by that. I just need the right couple, right? I use a copula, that's it. So the answer is this is universal. I mean, you can create any marginal. Now, where does it make sense, or whereas it's going to fit the data well, that's a different story. But in principle, you can create any marginal.
Okay, thank you. I think his questions are done. I have a few questions myself. So you suggested first that if you want to be on the safe side, maybe choose L big enough and put kind of a stick breaking pry on the weights. So you zero them as they become far away, something like that.
Yeah, okay. So that is an approach that you can take. We haven't done it with the stick breaking. We haven't done it we have not done it with a sparsity inducing prior of the weights. But that is in my to-do list. We have done it just with priors that concentrate a lot of mass on large weights and very, very little mass on small weights. But sure, that is a possibility, and I think it would be very nice to look into that.
Yeah, one interesting thing about the method you presented. So it becomes very flexible if you use copula, because as you said, you have also a framework to construct bivariate distribution with any marginals you feel like. It's very flexible. It's nice, right? But then you have bivariate copulas. I think the copula structure is how you will measure the dependence among the observations, right? So if you put a Gaussian copula, that's traditional, it scales to multivariate, but you don't need to do that because you're dealing with the bivariate, and then you have Archimedean copulas, all kind of copulas that doesn't scale well for large dimensions, but for bivariate, they are very intensive and they have very different dependence structure, even could be for max stable stuff. So this choice so you can construct anything, but the choice of the copula is very important in your model, right? That's very essential.
Yes, and in fact, I want on my to-do list. There is the possibility of leveraging the copula to obtain asymptotic dependence, and possibly, I love extreme value theory, right? And so I want to use these spatial models for spatial extreme value theory modeling. Right? That's what I would love to do. And it doesn't seem to be particularly difficult to do. I mean, you can have GeV marginals, and with the right copula, you can actually have asymptotic dependence, and you can control that asymptotic dependence in a way that is spatially varying. We haven't done it, but it's to me like a low-hanging fruit.
Interesting. So I could keep on asking questions forever, but I would just ask the last one, and before I thank you again. So the NNGP, not MP, the one you suggested, right? Originally, I think was first the motivation you saw, because it's a process. They argued there in the paper that that's a non-stationary process by essence, and it's used to approximate the stationary process. Is the N, and so they show that. I never seen any paper showing if the NGP, which is non-stationary, is useful to also approximate non-stationary process. Could be, I don't know. But do you think the NNMP, besides this flexibility of moving away from non-Gaussianity, can also be used to approximate non-stationary process? I'm assuming it will not be stationary as well.
Okay, so
stationarity in the rows, right?
Yeah.
Things.
Okay. Fine. So first order stationarity in the sense of marginal. It's either trivial, right, or non-existent. I mean, in the sense that every location will have the same marginal if you don't make any of the parameters of the bivariate distributions location dependent. I mean, if, for example, if you're using a Gaussian and your row doesn't depend on location, then marginal is Gaussian and is the same Gaussian for everybody. So the process, first order stationary trivially, right? Everybody, essentially, all the observations have the same Gaussian distribution, which is not very interesting, but fine. But that's a property. Now, second order and higher order stationarity, very hard to explore, because essentially the covariance, I mean, okay, so we went into some very specific structure when the correlation is linear and blah, blah, blah. So there are some special cases where we were able to come up with some recursive equations to calculate the spatial correlation function. But generally speaking, it depends on a complicated mixture. It's very hard to explore the properties of that thing, and that is one of the prices you pay with this. Right?
Yeah, because that's sometimes interesting to have the range and so on. They can be useful in some applications that.
Really no, absolutely. And I hear you, and.
But you cannot win everywhere, right? I totally agree with you. It's flexible.
I acknowledge it as a limitation of the framework. That unfortunately, the exploration of the properties of the correlation, the spatial correlation, and those things is difficult. You can do it empirically. I mean, you can fit the model, and then you run your thing, and then you do your plots and stuff like that. But theoretically, very hard.
That's the hard part. Yeah. Okay, so thank you, Bruno, again for accepting our invitation. It was a pleasure. Very interesting work. If you can stay a few minutes after I finish the transmission online, I want to talk to you real quick. Thank you very much. Thank you, everybody, for the questions and for the audience. And hopefully, Bruno, you will see Bruno in Brazil. I'll probably do an invitation for him to come soon. So hopefully you can meet him in the department at some time.
That would be fantastic. Okay.